Related to this electrical noise phenomenon, it should be noted that a motor paired with a motor drive must be inverter rated. An inverter rated motor has several design considerations such that performance and longevity of the motor are optimized. First, an inverter rated motor must remain cool even when operated at low speeds, and may include enhanced heat dissipation surfaces or even a separate blower. Additionally, inverter-rated motors also include upgraded insulation and incorporate additional design elements to withstand any high-voltage spikes. Let's put aside the inner workings of a motor drive for now and examine general characteristics of motor drives. This might seem overwhelming at first, since some of it comes with associated baggage that may or may not be in your possession at this time. Not to worry though, since I plan on discussing some of these characteristics in greater detail in later supporting lectures. For now, let's consider this a general inventory, and if something is pertinent to our discussion right now, we'll pick it up and examine it, and if not, we'll check it back in the pile and pick it up later. Let's do this inventory in small chunks so we're not overwhelmed. Motor drives are specified using several different characteristics, notably rated input voltage and current, rated output voltage and current, acceptable power rating of the motor under direction, and apparent power output of the device. Input voltage is that supply voltage necessary to operate the motor drive, ordinarily including acceptable minimums and maximums, typically expressed as plus or minus an acceptable percentage. Most motor drive manufacturers divide their offerings into three general product classes: three-phase 200-volt class devices, including three-phase AC distribution systems with nominal 200 to 240-volt values, three-phase 400-volt class devices, including three-phase AC distribution systems with nominal 380 to 480-volt values, and single-phase devices. By the way, these are arbitrary distinctions. Certain manufacturers may divide this into more or less classes and offer motor drives that operate using higher voltages. One of these input classes may jump out to you as an oddity, that of motor drives with single-phase AC input. But yes, it's true. There exist motor drives that make use of single-phase AC input. Returning to our earlier summary of the internal workings of a motor drive, recall that a motor drive can be thought of as two back-to-back power electronics devices: a rectifier, being an AC to DC converter, and an inverter, a DC to AC converter, with a DC link in between. The point being that the inverter portion of the motor drive largely does not care how the DC got there in the first place. All it needs is a grocery bag full of DC to whip up three-phase AC output with an adjustable frequency of magnitude. Motor drives intended to operate using single-phase AC simply use a single-phase AC to DC rectifier in the front end rather than a three-phase AC to DC rectifier, as for those devices intended to operate using three-phase AC. Both these devices use the same DC to three-phase AC inverter on the back end. Additionally, there exist flexible motor drives that can make use of both three-phase AC and single-phase AC depending upon mode. This feature is extremely cool, especially for light industrial users and small business owners without ready access to industrial three-phase AC. At business startup, one can just run the motor drive off commonly available single-phase AC. At a later date, when you're a legitimate player and have made enough money to install proper three-phase AC, you can simply toggle the operational mode of the same motor drive and continue operations as previously. Input current specifications relate the current draw when the motor drive is operating the motor under its direction at rated conditions. Keep in mind, rated conditions is a snapshot of a single point on a motor's operational curve. If the motor is experiencing less than rated conditions, current draw will be less. If the motor is experiencing more than rated conditions, current draw will be more. Greater than rated conditions is an overload, and if sustained for any length of time, might damage the motor. Luckily, motor drives often include sophisticated overload detection and protection mechanisms we'll examine later. Output voltage and current specifications are just the opposite, being the voltage and current output of the drive. Given motor drives are capable of varying frequency and magnitude, this entry in a motor drive datasheet may specify maximum magnitude and frequency. A typical small general-purpose motor drive might be adjustable up to 100 Hz. However, there exist special-purpose motor drives for exotic applications like centrifuges used to enrich uranium that can output at frequencies of 600 Hz or higher. For obvious reasons, these are export-controlled devices and not something you pick up from your local electrical supply shop. Those of you familiar with the history behind the Stuxnet cyber attacks in 2009-2010-ish will note that Stuxnet specifically targeted motor drives capable of this feat. But that, as they say, is another story entirely. Power ratings for motor drives are typically specified using two entries, one being the rated output mechanical power of the motor that is intended to be controlled, and 2, the apparent power output of the drive itself. An example might be a 400-watt motor drive capable of producing 1 kVA of apparent power. This entry means that the drive is intended to operate a motor capable of producing 400 watts of mechanical power output. However, the motor drive is capable of producing 1 kVA or 1000 volt amperes of apparent power, which, if you recall, is the vector summation of real and reactive power. At risk of opening up a barrel of rage-infected monkeys concerning apparent power, consider a motor that produces 400 watts of usable mechanical power, yet consumes 500 watts of real power, and let's say 400 volt amperes reactive of reactive power. This corresponds to an apparent power consumption of approximately 640.3 volt amperes and is inside the range of the specified motor drive. When we look at this using a chained system efficiency perspective, note that the motor is squandering 100 watts of available real power due to inefficiencies. The motor would therefore have an efficiency rating of 400 out over 500 watts in, or 80%. Additionally, note the motor drive itself may be squandering some input. Let's say to produce the necessary 640.3 volt ampere output, the motor drive itself might necessitate consumption of 710.6 volt amperes comprised of 550 watts of real power and 450 volt amperes of reactive power. This means that the motor drive itself is wasting 50 watts of incoming real power due to inefficiencies. The motor drive would therefore have an efficiency rating of 500 watts out over 550 watts in, or 90.9%. This is to say nothing about power factor nor power factor correction, which, as they say, is yet another barrel of rage-infected monkeys I wish not to open at this time. More to the point of this lecture, a motor drive manufacturer may specify efficiency rating of the drive, in this case 90.9%. Additionally, motor drives are generally specified using dimensions, enclosure specifications, and acceptable environmental conditions. Another general means of classifying motor drives is the control method employed. Motor drives are ordinarily classified as volts per Hertz drives or flux vector drives. Flux vector drives can be further subdivided into sensorless or closed-loop vector drives. This is a topic I am purposely tiptoeing around in the interest of expediency. We'll examine the details about these control methods in later lectures, but for now, the short summary will have to suffice. Volts per Hertz drives vary the magnitude of the output voltage. Sensorless flux vector drives can also vary the magnitude of the output voltage in addition to monitoring the phase angle between voltage and current. Closed-loop vector drives can do everything a sensorless vector drive can do, but are also intended to operate with an encoder feedback device that monitors a motor's actual position and speed in real time. Like I said earlier, let's gently put this topic back in the pile and back away slowly until we've got some free time to punch this tar baby to death. Moving on, motor drives may also be specified with respect to certain functional and control specifications, like soft starts, acceleration and deceleration times and patterns, overload current rating, instantaneous overcurrent protection, carrier or switching frequency adjustment range, and starting torque. Motor drives may also be specified with respect to protection functions, like overcurrent, overvoltage, undervoltage events, thermal errors, overload limits, memory errors, communication errors, overvoltage suppression during deceleration, momentary power outage write-out, disconnection and bypass means, and emergency cutoffs. Motor drives may also include handy bonus features or options like jogging operation, PID control, torque boost functions, fault monitoring, whether or not the drive includes a regenerative braking unit or braking resistor, whether or not the drive is capable of performing DC injection braking, and whether or not the drive includes accessory input and output filters to reduce noise, or line and load reactors to suppress harmonics. Motor drives may also sport optimized design features for specific applications, including but not limited to constant torque applications, variable torque applications, shock or impact loads, constant speed applications, or super high speed applications like production of enriched uranium using a centrifuge. Finally, motor drive specifications include details about means of communication, including the type of communication port, the drive programming method, diagnostic indicators and alarms, and the number of type of digital and analog inputs and outputs. Allow me to briefly comment on drive programming and communication configuration before we bring this lecture to a close. Sorry this lecture is getting a little long, but I feel a proper introduction to motor drives should encompass this base material. I promise later lectures on motor drives will encompass less material, but do so in a more, shall we say, intense fashion. Stay sharp and be sure to warm up and stretch beforehand. Anyways, programming a motor drive is essentially the means a technician walks through all those parameters we previously discussed and sets it up so the motor drive does what it's supposed to do. Drive programming can be a complex and tedious affair because very often the actual process requires intimate knowledge of a specific motor drive's decision tree and navigation within it, using the extremely limited number of buttons and the extremely small display panel available on the operator's interface. To anyone who has hacked their way through this thick, confusing jungle, believe me, I feel your pain. To ease this burden, some manufacturers offer offline programming software, allowing a technician to use a regular PC and far easier means of navigation to program and even simulate operation of a motor drive. Once the program is complete, it can then be downloaded to the motor drive and saved. A properly pre-configured motor drive consists of a number of user-adjustable parameters that vary from manufacturer to manufacturer and drive to drive. While a complete listing would both be tedious and pointless, I tend to break parameters into several broad categories, notably motor data, basic functions, advanced functions, conditions necessitating protection against, those conditions that warrant errors, and those parameters that need to be displayed, recorded, or sent, and communication configuration. Up front, a motor drive needs to be told what type of motor it's driving, since motor drives ordinarily lack the motivation to pick up the phone and ask the motor out on a date and spend some time getting to know it. Often this step simply necessitates a technician read the intended motor's nameplate and input this data into the motor drive. Critical data often included in this preliminary meet and greet are the motor's rated mechanical power output, base frequency, typically 60 Hz in the US and 50 Hz in the EU, the number of pole pairs per phase, rated speed, full load current, supply voltage, and depending upon the specific drive and application, unloaded or magnetizing current, and DC stator resistance. The unloaded or magnetizing current is, as the name implies, the current drawn when the motor is free spinning without a load. The DC stator resistance value is often critical for those motor drives capable of DC injection braking. The bulk of the remaining steps in programming a motor drive are those application-specific settings that make motor drives so useful and versatile, as well as the upper and lower limits for protection and error detection. Long story short, it's setting up the remaining parameters of the motor drive. Examples of basic and advanced function parameters might include default rotation direction, preset speed, acceleration and deceleration time, acceptable minimum and maximum speeds, dynamic braking methods employed, carrier frequency, PID gain values, or any other wondrously complex operation sufficient to achieve the desired results. Examples of protection and error parameters might be overload limits, overcurrent suppression functions, instantaneous overcurrent values, overvoltage values, and so on. Examples of parameters that might need to be displayed, recorded, or sent somewhere might be the output frequency, the output voltage, the runtime, or other pertinent data that needs to be communicated with the outside world. The last programming parameter category, communication configuration, requires a bit of explaining, as well as an accompanying diagram. A simplified block diagram of a generic motor drive intended to operate with three-phase AC might look something like this. The motor drive obviously has three-phase AC input terminals specified L1, L2, and L3, or sometimes R, S, and T, depending upon country of origin. Additionally, it has three-phase output terminals specified T1, T2, and T3, or sometimes U, V, and W, depending upon country of origin. Between the three-phase AC input, one might observe external disconnection means like a circuit breaker, as well as any accessory external input filters or line reactors. Between the three-phase AC output and the motor under its direction, one might observe any accessory external output filters or load reactors. Additionally, a motor drive necessitates an external power supply connection to power up the internal electronics that make the rectification, inversion, and control process possible. For those motor drives necessitating the external braking resistor, you might see braking resistor connections. Additionally, motor drives may include supplemental bypass contactors that I've not included in this diagram. If our purpose is to discuss direct operation of a pre-programmed motor drive at the point of use, we can kind of stop right here after we include a couple buttons and a dial, along with a super tiny, dimly lit display on the front. Note, some drives make use of an interface linked to it via a cable. We'll come back to expand this block diagram in a moment. To directly operate a motor drive, a technician uses the keypad interface to directly stop, start, change direction, adjust speed, and read parameters. If a motor drive has been properly pre-configured using the above summarized programming procedure, an untrained operator really only requires limited interaction with the device and does not need to familiarize themselves with the programming procedure nor navigating the decision tree. An operator wishing to start the pre-programmed motor drive simply presses the big green start button, and an operator wishing to stop the motor drive simply presses the big red stop button. If an operator wants the drive to go faster, they turn the dial one way. If an operator wants the drive to go slower, they turn the dial the other. Motor drives may also include password protection that prevent untrained operators, under the false assumption that they are trained operators, from haphazardly adjusting the desired parameters. Expanding upon this block diagram, motor drives also include accessory digital and analog inputs and outputs that allow the motor drive to remotely interact with a larger system without the necessity of constant and direct human supervision. Digital inputs and outputs are those that have two mutually exclusive states, either on or off, that can never be a little bit of both or halfway in between. Ordinarily, a motor drive includes several fixed function digital inputs and outputs, as well as one or more multifunction digital inputs and outputs that are customizable by the user and can assume many different roles depending upon the needs of the process. Let's say our simplified block representation of a generic motor drive includes two fixed function digital inputs, two multifunction digital inputs, two fixed function digital outputs, and two multifunction digital outputs. Those inputs and outputs specified as fixed function, as the name implies, perform that function only and are not customizable. Let's assume fixed function digital input 1 is permanently assigned the start input that starts the motor using the pre-programmed parameters. Let's assume fixed function digital output 1 is permanently assigned the run output. Anytime the motor drive is running, this digital output would be asserted. In contrast, those inputs and outputs specified as multifunction, as the name implies, are user customizable. For example, multifunction digital input 3 could be programmed to act as a momentary jogging input today, and then when the motor drive parameters are reprogrammed, act as an enable signal for PID control input tomorrow. With respect to multifunction digital outputs, multifunction digital output 3 could be programmed to act as a constant speed arrival signal today, and then when the motor drive parameters are reprogrammed, act as an overload warning tomorrow. Long story short, the number and range of functions capable of being assigned to the multifunction inputs and outputs are direct reflections of the utility and versatility of motor drives for numerous applications. Analog inputs and outputs, in contrast, are those signals that are continuously variant proportional representations of a quality and can take any value inside a predetermined range. An example of an analog input might be a continuously variant external potentiometer used as a frequency reference input. This is often called the speed pot. As an operator turns the external speed potentiometer adjustment knob, the analog input signal proportionally varies, thereby giving an operator or system a degree of fine control in the motor drive's resultant frequency and thus motor speed. Note we're assuming the motor drive itself is capable of supplying a positive 10-volt power and common connection to the potentiometer, which may or may not be the case. This analog input signal need not come from an operator adjustable device like a speed potentiometer, but could also be some automatically generated incoming analog signal or transducer output. An example might be an incoming analog signal from a PLC. An example of an analog output might be a proportional representation of the real-time output frequency. This is sometimes called the frequency monitor signal and is often used for feedback, closed-loop control purposes. Note that analog signals could be voltage or current signals proportional to the represented quantities. In addition to digital and analog inputs and outputs, motor drives often include sophisticated communication ports that allow not only programming, but also real-time control and monitoring of a motor drive's operation. Communication ports may make use of any number of open or manufacturer-specific protocols that may or may not be compatible with one another. Certain motor drive applications, in fact, do not make use of any of the accessory analog and digital inputs and outputs, but rather handle all incoming and outgoing communication control via the communication port. It should be noted that accessory inputs and outputs of communication ports allowed a motor drive to interface not only with traditional hardwired switches and indicators, but also PLCs, themselves a reprogrammable and fully customizable control system. The reprogrammable nature of both motor drives and PLCs make them extremely attractive options for advanced systems. Alright, we have just got to set this lecture down for a landing, because I'm just about to fuel, and I'm certain that tiny head of yours is just filled to the brim with knowledge and at risk of overflowing. Luckily, we have arrived at a convenient breaking point. Like I said earlier, much more about specific motor drive applications await. In conclusion, this lecture took a brief look at motor drives, a power electronics device that vary the speed and torque of a motor under its direction by varying the supplied voltage, magnitude, and frequency. We reviewed those properties that influence synchronous speed, examined antiquated methods of speed control, discussed rectification, inversion, and filtration. Additionally, we examined common motor drive specifications and parameter programming, and finally we examined a general block diagram of a motor drive, including fixed and multipurpose analog and digital inputs and outputs. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.